Hi, I'm Rebecca. In this presentation, I'll be talking about graph threading, which is joint work with Erik Demaine and Yael Kirkpatrick. Many artistic practices, such as beadwork and himili, involve threading tubes with string to form various intricate patterns, shapes, and structures. On a more practical front, threading offers a promising mechanism for constructing deployable structures capable of transforming between distinct geometric configurations. A collection of tubes, loosely woven, can be compactly stored and then swiftly deployed into target configurations by merely pulling the string tight. A demonstration by Allison Martin is shown here. I also spent some time exploring this mechanism with Tomohiro Tachi this past summer. An early prototype is shown on the right. The design of both the geometries of these structures and the routing of string through them requires considerable thought. In this talk, we will formally unsolve the problem of efficiently threading a single string through a collection of tubes so that when the string is pulled taut, the tubes connect or meet as intended. In more graph theoretical terms, we want to thread a string through a collection of tubes to mimic the connectivity of a given graph. We take as input a connected graph, G, with maximum vertex degree 2. Here, as an example, we have the graph corresponding to the tetrahedron from the demo in the prior slide. Each edge represents a tube, and each vertex represents a junction where the tubes incident to the vertex ought to meet. The threading of a graph is a closed walk through the graph that visits each edge at least once. This walk also must induce a connected junction graph at every vertex V. The junction graph of V has a vertex for each tube incident to V and has an edge between two vertices every time the walk visits V immediately in between traversing those tubes. We underscore that a threading must induce junction graphs that are connected. That is, these junction graphs must contain at least a spanning tree. We see that this is indeed the case for the junction graph circled on the slide. It is a cycle. Next, we note that this walk, that is our threading, must not have any U-turns. That is, when exiting one tube, the walk must next enter a different tube. It can't immediately return to the same tube. The number of times the threading visits an edge UV is called the count of UV, denoted as XUV. The length of the threading is the total number of edges visited by the threading, or the sum of the counts over all the edges. We can easily compute a threading of length 2m by taking a tour through the graph so that each edge is visited twice, forbidding U-turns. Each junction graph would be exactly a cycle. However, can we do better? In most applications, we want to save on material and labor, and so it's natural to want to minimize the length of the threading. In the case of threading a tetrahedron, we can indeed do better. On the left, we have a threading of length 8 rather than the 12 from the double threading. For the remainder of this talk, we will discuss the problem of finding the optimal minimum length threading of a given graph. Some of our results are as follows. We have a polynomial time algorithm for computing the edge counts of an optimal threading. We also give a polytime algorithm for constructing an optimal threading from these edge counts. In our paper, we provide several improved algorithms for special cases, specifically when the input graph is cubic, and also when we are allowed only two traversals for each edge. We also provide some upper and lower bounds for optimal threadings. In this talk, we will show that we can express a threading in terms of a set of local constraints. We show that these constraints are necessary and sufficient for a threading by giving a constructive proof. We demonstrate an algorithm for constructing a global threading from local solutions. And to solve for these local solutions, we rely on a reduction to perfect matching. Okay, let's discuss the per vertex and per edge properties that our threading must satisfy. A local threading of a graph consists of a set of edge counts. So recall that a count of an edge is the number of visits the walk makes to the edge. So these set of edge counts must satisfy 4 constraints. First, each count must be greater or equal to 1, since each edge must be visited at least once. We note that a threading increments the count of 2 edges incident to a vertex every time it traverses that vertex, because it must come in and go out of that vertex. Therefore, the sum of the counts of all edges incident to a vertex must be even. Here we show a negative example where the sum is 5. So we note that no matter how we route the walk to satisfy the edge counts, there will be a thread that enters a vertex with nowhere to exit to. The third constraint forbids U-turns. If an edge UV is threaded, say, k times, then the sum of the counts for the remaining edges incident to V must be at least k to supply these visits. On the right, we show an example where the top edge is to be threaded 5 times. However, there are only 3 threads from the remaining edges available. So this is impossible without allowing for U-turns. Next, because each junction graph must be connected, it has to have at least enough edges to form a spanning tree with dv minus 1 edges, where dv denotes the degree of vertex v. Therefore, the sum of counts of edges incident to v must be at least twice this number. In this case, where there are insufficient visits, the junction won't be connected. Whereas here, with sufficient visits, we can create a traversal of the thread that ensures connectivity. We shall now argue that these local properties perfectly encapsulate a global threading. That is, once we solve this linear program, we can obtain a threading from it. So here's a game plan. Given a solution to local threading, we shall first construct a connected junction graph at every vertex based on the solution. Then we will find a threading from the resulting collection of junction graphs. Okay, let's demonstrate the construction of a connected junction graph. So say we're given a local threading. This means that we have a count associated for each edge of a graph. In this example, it's 2, 1, 2, 1 for the vertex shown. For this talk, we restrict to the case when constraint 4 holds with equality. That is, the sum of the counts of a vertex is equal to 2 dv minus 1. In the paper, we show the generalization. To begin construction of the junction graph for this example, we have a vertex for each tube incident with a junction with desired degrees equal to the counts. The claim is that we could construct a tree on these vertices that satisfy these given degrees. The algorithm is as follows. In each step, we choose 2 vertices, one with degree greater than 1 and the other with degree 1. This is always possible given a restriction on the degrees, which imply that their average values is strictly between 1 and 2. We connect these vertices with an edge and then decrement their degree counts. And we'll repeat this procedure until we arrive at the base case. In the base case, only 2 vertices remain, each with desired degree 1. So we just have a path between them. And so we have a tree. Given a local threading, we shall construct a junction graph at each vertex. The next step is to find a closed walk in the graph that has no U-turns and corresponds to these junction graphs. First, we take the union of all the junction graphs created. Then, in the resulting graph, we find an Euler tour, a closed walk that visits each edge of the graph exactly once. An Euler tour is guaranteed since each vertex of the graph has even degree. To ensure that U-turns are avoided in the threading, we enforce that the Euler cycle does not consecutively traverse 2 edges of the same junction graph by reduction to forbidden pattern Euler tours. In the paper, we show that for an optimal threading, we could convert a local threading to a global threading in linear time. Now we'll take a quick look at bounds. As discussed, we can employ a double threading strategy by assigning every junction to be a cycle. This threading results in each tube being traversed exactly twice, totaling a length of 2m. So the optimal threading has length at most 2m. We can approach this bound up to an added constant by considering graphs with long sequences of bridges. Each bridge edge needs to be traversed at least twice to close the loop. Okay, so we've talked about the maximum length of an optimal threading, but what is a minimum possible length? The answer is 2m minus n. It occurs in the case that each junction graph is a tree. We call a graph threading with length 2m minus n a perfect threading? Not all graphs have perfect threadings. In this example, we have bridges connecting otherwise disjoint components to a central vertex. The only way to pass between two of these components is by traversing through a bridge, and so we need to traverse each bridge at least twice. Therefore, the central vertex must have a junction graph that contains at least a cycle. Now we show how to determine if a perfect threading exists for a graph, and we demonstrate an algorithm to find the local threading corresponding to a perfect threading in this case. While we speak only of the special case here, the paper shows how to find the optimal threading if there isn't a perfect threading. For a perfect threading, constraint 4 holds with inequality. We'll denote this modified constraint as C4 star. It is easy to verify that a local threading is a perfect threading if and only if it satisfies constraint 1 and this modified constraint C4 star. C2 follows immediately from C4 star because the sum of counts is even. We can rewrite C4 star and combine it with C1 to show that C3, which forbids U-turns, indeed holds. Now, let's consider the problem. At every vertex V of the graph, we want to distribute 2 dv minus 1 units, or threads, amongst the edges incident to it. This is the question. We know that each edge has to be threaded at least once based on constraint 1. Therefore, the problem reduces to distributing the remaining dv minus 2 threads. Our approach is to construct a graph H that has a perfect matching if and only if for every vertex V, we can distribute dv minus 2 units amongst its incident edges. A perfect matching in a graph is a set of edges of the graph that covers all the vertices and has no common vertices. Okay, we show this reduction. Consider our input graph G. For each edge UV, we create a number of disjoint edges. This number is a minimum of the vertex degrees of U and V minus 2. In our example, for the edge highlighted in yellow, both of its endpoints are of degree 4, so we create 2 disjoint copies of this edge. Next, we create dv minus 2 vertices for each vertex V, shown in red. This is going to be the key gadget in forcing the distribution of dv minus 2 units at each junction V. Finally, we form bicliques at each junction connecting all the red vertices with all the blue vertices. The edges are shown in purple. We note that for each purple edge that is in the matching, and there needs to be dv minus 2 of them for each vertex V, it implies a blue edge that is incident to the junction that is not in the matching. So the idea is that we increment the count of the edge in G corresponding to that blue edge. More formally, XUV is defined as follows. It is 1 plus the number of blue disjoint copies of UV that is not in the perfect matching of H. And here we show a perfect matching of H in bold. And this is an example threading that we could construct from the resulting counts from the matching. In the paper, we go into detail proving that a graph G has a perfect threading if and only if H has a perfect matching. And of course, we generalize to all graphs where perfect threadings may or may not exist. So what are our next steps? We'd like to develop tighter bounds depending on the properties of the input graph. We'd like to come up with more efficient solutions to the general problem. We'd also like to look at angular metric graph threading. We've learned that the frictional force required to pull a string through a series of tubes increases exponentially in the sum of the absolute values of the turning angles. So therefore, it is natural to want to find threading routes that have minimum total turn. And that's it for my talk. Thanks so much for listening.